So to review the double slit experiment, when we shoot electrons at a screen, we end up with this interference pattern. Now, the inference we can make from that, if we see an interference pattern, we can infer that there's wave-like behavior. And since we've already seen particle-like behavior from electrons, like for example in cathode rays, electrons must exhibit both wave and particle type behavior. So wave-particle duality of electrons. So based off that experiment, we can now think of electrons not as particles, but as waves. So if we think back to that Bohr model, now that Bohr model is not really the best model because still those electrons orbiting around the nucleus should be emitting EMR. However, if these electrons exist as standing waves, you can see these waves at the top, this green, red, and blue wave. That's an example of a standing wave, resonating back and forth. Well, we can think of electrons as that way as well. And only electrons with certain wavelengths wrap perfectly around those Bohr energy levels. If the wavelength of the electrons are too big or too small, they would add destructively and collapse. But if it fits the radius, the electron as a wave, like in this diagram on the right, is actually very stable. So if you follow that theory, the electron stops being a particle orbiting the nucleus at a certain point. Instead, an electron's mass and charge can be thought of as spread out, as a standing wave around the nucleus. So the electron's not really at any one position as a particle, it's everywhere as a wave. So even as a wave, though, the electron exists mostly right near the Bohr orbit. There's a probability associated with that wave, and where you would find the electron at any moment. So quantum mechanics takes the behavior of the electron and turns it into a mathematical model. And that mathematical model shows where the electron's likely to be found based off of its wavelength and the energy that it has. So this now is what some people call the electron cloud model, because those electrons exist as a cloud outside of that nucleus still at the Bohr energy levels, but they exist as standing waves. Now we can do some math with this idea as well. This is an example of a particle accelerator at Fermilab. It's used for a whole bunch of different experiments. The part that we're going to talk about is this one, this linear accelerator. Now, this whole apparatus uses a whole bunch of different magnetic and electrical fields to shape and accelerate different beams. Now, in this linear accelerator, that part down there, it accelerates protons near the speed of light, so like 99% the speed of light, or a speed of 0.99 c. It's 99% the speed of light. Now, if we have very small protons moving at that speed, de Broglie's hypothesis tells us that it should be exhibiting wave-like behavior. And that wave-like behavior should be evident. So we can actually calculate the de Broglie wavelength for those protons using this equation that we have that relates wavelength and momentum. Because those protons are going to have mass, they're going to have speed, they're going to have momentum. We can use this equation just like we can use it for photons to find out more about the wave nature of these particles. So momentum is just mass times velocity. And then I can plug in different values for that. I'm going to use the 6.63 value for Planck's constant, because I want to find a wavelength in meters. So it's joules per second. The mass of a proton is 1.67 times 10 to the negative 27 kilograms. And the speed, so the velocity, 0.99 times the speed of light, 3.00 times 10 to the 8 meters per second. I do that calculation, and I find the de Broglie wavelength of those protons in that accelerator to be 1.34 times 10 to the negative 15 meters. So we can do calculations. We can find out more about the wave nature, the particle nature of these different photons, different particles, using these sets of equations that we have.